All right, the last section we're going to cover is 9.2 on linear regression, and this is really a continuation from section 9.1. So in 9.1, we focus on verifying that there actually was a relationship between two variables and that relationship was significant. So this is the next step. So once you've already verified that there is a linear relationship that is significant, the next step is to go ahead and determine the equation of the line that models the data. This line is called a regression line. Its equation can be used to predict the values of y for certain given values of x. So consider the scatter plot in the line shown below. For each data point, they're using DI just to represent D for data and I just for the different data points, representing the difference between the observed y values and the predicted y values. So those data points here, that D that you're seeing, is the difference between what we observe and what we predict. So the regression line these are your predicted values, basically. Okay. And then here you actually have the actual data points. So the D here then is actually the distance between the actual data points and the predicted values. These differences are called residuals. They could be positive, negative, or zero. When the point is above the line, like these are here, then these are going to be positive. So these will be positive. And when the point is below the line, like this one here and this one, these are going to be negative. When the y value equals the predicted value, then that d sub I is 0, meaning that it lies exactly on the line. Of all possible lines that can be drawn through the set of points, the regression line is the line for which the sum of the squares of all residuals is minimum. Okay, so that's what we're doing with the regression line, is we're minimizing really sort of these distances between the residuals or the distances, between the observed values, and the predicted values. So getting those residuals. The regression line is also a line of best fit. It's the line for which the sum of the squares of the residuals is minimum. So again, it's a best fit line, meaning it's the best line we're going to get to help us predict or model the data. And it's actually formed using the same general rule that you've seen before from your algebra classes of y equals mx plus b. So remember in a linear form that your m is equal to your slope and your b is equal to your y-intercept. That's the point 0, b. So we're going to use this idea, this point slope form here, to actually help us find the regression line. Now, the equation of the regression line allows you to use the independent variable x to make predictions for the dependent variable y. And again, it uses that same mx plus b format. We do use this little y hat here to indicate that it is the regression line, so it's a predicted line rather than the actual raw values. Now, it's kind of hard to find or tedious to find by hand, but we can do it. And the formula for the m is this, and the formula for the b is this. Now, I'm going to go back to that same example that we did before by hand as well, and I'm going to bring out our values, because if you already have done all that work, then we can still use that same piece here. So let me bring that out for you guys. So remember way back a couple of videos ago, we did all this work by hand. So it's the same example. So I actually do have all those key values that I need, and I'm just going to go ahead and rewrite them in on this page and use those in our work. So we had found that the sum of the x's is 22.9. We already found the sum of the y's was 5,129.7. Some of the xy's were 14350.74. The sum of x squared was 65.49. And the sum of the y squared, this was a large number, was 3,312,080.89. So again, I'm just using the work that we did from section 9.1 because we're going back to that same example just to save us a little bit of time here. But if you have to, you'd have to find all these values again if you're doing it by hand. So now that we have those values, I'm going to use our formulas and plug in. So let me just come down here and rewrite this. So our m is n times the sum of the xy's minus the sum of the x's times the sum of the y's all over n times the sum of x squared minus the sum of the x's squared. And our b is y bar, so that's the mean of the y's, minus m times x bar. So you're looking at the sum of the y's over n minus m times the sum of the x's over n. Now I'm using all these values up here in my formula. And again, we calculated these back in 9.1, so if you need to review that video, please do. I have 10 data points here. So I have 10. The sum of my xy's was 14,350.74 minus the sum of the x's was 22.9, and the sum of the y's was 5,129.7. My n is 10. My sum of my x squares was 65.49, and then minus the sum of the x's is 22.9, and then that value gets squared afterwards. And what you get here is about 199.534600. And again, you can try that calculation at home. And it's just taking your time. So you're just multiplying, subtracting, don't forget to square here, and just really taking your time cleaning that all up. Now for your b, okay, we have the sum of the y's, which was 5,129.7, and I have 10 data points, minus. Now for your m, you want to put this whole value in there. So I'm going to run out of room here, but you want to use as many decimal points as you can. Okay. I don't really need the 2 zeros there, so I'm going to multiply that, and then I have that times my sum of my x's, which is 22.9 over 10. So we get, let's see, about 56.036. So my equation then is mx plus b, so it's y hat equals 199.534, I'll say 6x plus 56.036. But again, doing this by hand really does take a lot of work. So we can do it. And again, if you need to review these steps, go back to the section 9.1 video, and you can do this process by hand. Although I'm going to show you right now how to go ahead and find that on the calculator. Now again, so let's scroll down a little bit here. So don't forget that first you do have to enter your data, your x values in L1 and your y values in L2. So you have to press stat and edit there first and actually enter all your data. Now I already have it entered because we've been doing the same example for a while now. So you can see here, if I hit my stat button and my edit, I do have my 2 columns already ready to go there. So we're going to just do the next step. We're going to press stat. We're going to go over to calc, and we've seen this one before. Make sure you press L-I-N, not L-N, so L-I-N-R-E-G. And then you do need to tell it the L1 and L2. So you're just going to enter L1, comma L2. So second 1, comma second 2. And that's enough. And if you hit enter, it's going to give you a whole bunch of different values. Now, what they're doing here, so if you look at the calculator, they have it set up like this, a plus bx instead. Okay. So actually, I apologize, I wrote this backwards. The a value, let me do this. The b value is the slope here. Sorry about that. And the a value is the y-intercept. So if you look here on your calculator, they're giving you the setup, and then they're telling you that A is 56.03, we'll say 6, and the B is 199.5346, like I had. So it's written a little backwards than what we're used to, but you do have that same sort of setup here. And if I just plug these values in, I'm going to go ahead and get that same equation. It's just written in a backwards format, but that's okay. Now that we have our formula here, we can go ahead and we can actually use this now to make predictions. So when correlation between X and Y is significant, then the equation of the regression line can be used to actually predict Y values for certain X values. You do want to be careful. Predictions are only meaningful for X values that are close to the range of observed values. So if you start choosing X values that are really far away from the original data set, then your observations are not going to be as good. So your predictions are not going to be as good here. So we do want to be careful. So let's actually go ahead and do an example. So we're going to use the regression equation for the gross domestic products and carbon dioxide example, the same one we've been doing. And I just rewrote it here. So they're using just 3 decimal places in each case. So we'll go ahead and we'll follow that same protocol. I know I used 4 decimal places here. And we're going to use this equation to predict the expected carbon dioxide emissions for each gross domestic product. So we're doing 1.2 trillion, 2.0 trillion, and 2.6 trillion. Now, one thing to note is the X values here do represent trillions of dollars. So for example 1, we're just plugging in X equals 1.2. So because the units actually match the X value calculations that we've done in our problem. So for the first one, we're just going to go ahead and we take our equation here, and we're just going to go ahead and replace that X with 1.2, just plugging it in like a regular equation, and we're going to go ahead and simplify. So you're going to multiply this first and then go ahead and add, and we see the value is 295.478. So for instance, this means that when the GDP, so gross domestic product, is $1.2 trillion, the predicted CO2 emissions are 295.478. And the units here, if you kind of go back, were million metric tons. Then we can do the same thing for B and C. So for B, our X value here is 2.0. So we just go ahead and we just plug it right in. And again, just using your calculator, you should get here about 455.106. And you have the same interpretation. So this time when the GDP is 2 trillion, the predicted CO2 emissions are 455.106 billion metric tons. And then for C, my X equals 2.6. So again, we're just going to go ahead and plug this value in. We're going to use our calculator, and you should get 574.827 for your result. So again, same sort of interpretation here, but this time with $2.6 trillion. And if I just go back to the data set that I've been using, so look at those X values that I had originally, right? I have 1.8, 1.3, 2.4, 3.9, 0.9, and so on. So they kind of range between, let's say 0.9, it looks like, and 4.6. So my values here are nicely in between the original data points. So these are all reasonable numbers to plug in. Remember, you want to stay close to the data set when you're estimating other values. So for instance, it would not be a good idea for me to plug in something like $10 trillion because my data set has values nowhere near 10, right? They end at 4.6. That's too far away. Maybe I could plug in something like 4.8. That could be close enough. But again, you just want to make sure when you're plugging in values that your values are close to what you see in the original data set. If they get too far off, then your predictions are not going to be good anymore.